Naveen, hello all of you. Hope I am audible. So I'm going to start the session. So we have completed the wire drawing operation, my dear. So in today's session, I'm going to discuss you the welding part, welding process that is very important, my dear. Welding technique, it is very important. Welding process. We have done all these things. Now let's move to the welding part, my dear. Metal joining process or welding, right? See. Audible, Naveen. Where are the other students, Naveen? I hope you guys are doing good. See, my dear. So, two topics are your numerical oriented topic, my dear. Next is your joining process, welding technology. Welding process, okay. See, what is this welding process? What is the definition, my dear? The definition of welding process is it is a process in which permanent joints are formed. Permanent joints are produced with or without addition of heat, with or without addition of pressure. Sometimes we use heat, sometimes we use pressure, sometimes we use plastic deformations. So different techniques. Sometimes we add filler material. So this is how you can define welding process. It is a process, it is a manufacturing process in which permanent joints are produced. It is a it is a manufacturing process in which permanent joints are produced with or without addition of heat. With or without addition of heat, with or without application of with or without application of pressure, comma with or without application of filler material. with or without application of filler material, right? This is actually definition of welding process. So in if you can recall the day one lecture of manufacturing, in that I have already classified, right, the different welding techniques. So the numerical oriented techniques are like your arc welding and as well as your resistance welding. So first today I am going to discuss you the arc welding and the various types of numerical which I am going to solve in this topic of arc welding. So let's start everyone. What is arc welding and their important numerical? Note down the definition first. Done, Mukul? Done, all of you? Mukul Manpure, Naveen, Navsi. See, arc welding and the principle of arc initiation. See, principle arc welding. In arc welding, first we are going to learn principle of arc initiation. How the arc is initiated. Arc principle of arc initiation. Okay. See everyone. Suppose this is your plate, my dear. This is your plate. These are the two plates which you actually want to join. This is your plate, my dear. And this is your electrode, right? This is your electrode, my dear. And this electrode is connected with a circuit. This is your negative terminal and this is your positive terminal, right? This is your negative terminal. This is your positive terminal. Okay. Now, the first circuit is called your open circuit. Remember that. What we call open circuit. Now, in this open circuit, the current is not flowing between the electrode and the workpiece. This is the electrode, this is the workpiece. Current is not flowing. Whenever you go into in any workshop, suppose you have taken electrode in your hand and the workpiece in another hand. If you try to start the welding is not possible at that moment. Still, it is connected with the electricity, but welding is not possible. Why? Because this medium is not ionized. Because there is no current flow between the electrode and the workpiece. So this is because it happens because the medium is not ionized. The gases present between the electrode and the workpiece are unionized gases. Right? This is your unionized gases. Clear? This is your unionized gases. Unionized. Unionized. Unionized gases. So to flow current between two systems, the medium between system must be ionized. Means there will be cation and anions. So in open circuit, guys, always remember in open circuit what actually happens. In open circuit, guys see, in open circuit what happened, the current, what we call it as a, what I am going to write in this, in open circuit we are going to write OCC. This is called your open circuit current. Open circuit current, right? And one is your OCV. This is called your open circuit voltage. So remember, my dear, whenever the circuit is open, the first case, and medium become unionized, then in that case, there is no flow of electricity between the, there is no flow of current between the electrode and workpiece. Therefore, in open circuit current, therefore the value of open circuit current is always zero, right? So remember that in this case, in this case, in first case, your open circuit OCC, open circuit current is zero, but open circuit voltage is not equal to zero. Voltage is there. There is a voltage between the electrode and the workpiece, but current is zero. Why zero? Actually, current is the flow of electrons, and electrons flow only in the ionized medium. That's why. Clear? So open circuit current is zero. So open circuit current does not play any role because it is zero. So we do not consider this open circuit current in the numericals. Okay, it is, its value is zero. Now, next part, to start the welding, guys. To start the welding, what we do? We actually try to ionize this medium. To get the medium ionized, heat is required. So from where we can get the heat? So we do short circuit. So the next circuit after open circuit, we make a short circuit. How the short circuits are made? See, if you connect the two terminals having some voltage difference, if you just connect the two terminals, suppose this is the gap, right? And it is going to get connected. Suppose it is going to get connected like this. If it is going to get connected, okay, understand this part. Right. So this part is going to get come in contact, right? So here what happened? These two terminals, is your negative and this is going to be your positive. Okay. So here this is your negative, this is your positive. Okay, my dear. So once this circuit get short, this circuit is called actually short circuit. Short circuit. When the two wires get connected, get touch each other, right? When two wires touches each other, that circuit is called your short circuit. In short circuit, both the wire comes at the same potential, right? So actually what happened here, whenever short circuit takes place, so you have seen so many times, you have heard in news that huge fire takes place in sometimes in hospitals, sometimes in heavy buildings, hotels, right? Why? What happened? So due to short circuit. Actually, due to short circuit, fires are produced, a strong amount of heats are produced, and that heat actually, whatever heat that is developed in the short circuit, so due to that heat, this medium get ionized, right? This medium now get ionized in terms of plus and minus, right? You can charges are produced, plus minus, right? So due to short circuit, medium get ionized, ionized medium, right? So in short circuit, actually what happened, my dear? Now both are at same potential, therefore here also SCC, short circuit current, short circuit current, and this is your SCV, short circuit voltage. Short circuit voltage, right? Short circuit voltage. So now here what happened? Both are at the same potential. Therefore, voltage, short circuit voltage becomes zero. But here a short circuit current, right? Short circuit current, that is your not equal to zero, because huge current flow. Whenever there is short circuit, huge current flow, and I square RT, when current value is more high, very high heat energy is released, right? Due to high current. Current is not zero, but the voltage, short circuit voltage is zero, my dear. So these two play very important role, my dear. One is your open circuit, non-zero, open circuit voltage, and short circuit current. Open circuit voltage and short circuit current, right? These two play very important role. Remember, guys, principle of arc initiation. This is your unionized gases. This is your ionized gases, ionized medium. Clear, all of you? Tell me. Tell me, all of you. I hope this part is clear. No, no, all of you. Very good, Naveen. Very good. Good, all of you. Good. Done till now. Done. Mukul Manpure. Very good, Mukul. I hope it is clear. Now, see, guys. Now, once this is done, now I'm going to make you the actual circuit, actual welding circuit. See, the welding circuit on the basis of these two. Now now this medium get ionized. Now we take the electrode apart from workpiece. See, welding circuit, if I am talking about. See, if we consider this welding circuit, this is your electrode, my dear. And this is going to be your workpiece, my dear. These two you want to join it, right? See, this is connected with the circuit now. This is your positive terminal, negative terminal, and this is your positive terminal. So here what happens, see, this is your negative terminal, this is your positive terminal. I am connecting it with a transformer. Suppose I am connecting it with a transformer, okay? AC power source, then there will be a transformer. So you can connect it with a transformer, no problem at all. Transformer will be like this. is a transformer. Okay, like this. So guys, now see, when you first you take this electrode at this point, then in short circuit this is called your open circuit. Next you touches the plate, that will called short circuit. Now you take the electrode apart. So now this medium get ionized. Now the medium present is ionized. When this medium is now ionized, and if it is your positive terminal, this is your negative terminal, then the workpiece, since workpiece is connected with the positive terminal, so a plus sign, positive sign appears on the workpiece and the negative sign on the electrode, right? What is going to be happen? This ionized gases attracts the electrode from attracts the electrons at the electrode towards the workpiece. So gradually, my dear, what is going to happen? Gradually, electrons get attracted from the electrode to the workpiece, right? It will be like this. It is going to attracted like this. Now the system become ionized, so it is going to attracted like this. And the flow, this flow of electrons in this ionized medium from the negative terminal to the positive terminal is called arc. That flow of electron is called arc. So this is actually called principle of arc initiation and arc welding. Now we need to understand some important point in this. Say the arc, this arc, whenever you see this arc, so there is a graph between this arc voltage and arc length, my dear. See, so that is the length, the distance between the electrode and the workpiece. Between that, the arc remains there. Arc is produced. That is called your arc length, right? So arc length, that's you can consider here. This distance is called your arc length in this, right? This is your LA, arc length, right? Or L you can assume, no problem. L. So guys, if you draw a graph between these two, voltage and arc length, suppose this is the voltage and this is your arc length A, right? L, sorry, L. So the graph is like this, my dear. The graph is like this, right? Y is equals to mx plus c, and the relation is V is equals to A plus BL. V is equals to A plus BL. V is equals to A plus BL, where V is your, remember that, where V is your arc voltage, in volt, and L is your arc length in mm, right? Always remember it is in mm. And A and B are constant. A and B are constant. Clear, guys? I hope this discussion is done. Note down, everyone. Clear, guys? Clear, all of you? Clear, guys? Good. Now see, my dear. Now, guys, see everyone. Next important part is, see. Now there is one another voltage, that is your now one more graph that is predominantly between voltage and current, right? Suppose this is the graph between V and I. See here, if this is the transformer, it is supplying a current of V, current of I, sorry. Transformer supplying a current I, and across the transformer, the transformer voltage is V. So how, what is the relation between the transformer voltage V and the transformer current I? You can see, my dear, the maximum voltage in any cycle is the voltage when the circuit is open. Circuit is open is your open circuit voltage. Open circuit voltage is the maximum voltage in any cycle. This is your OCV. And maximum current in any cycle is your SCC whenever short circuit takes place. If you join these 2 points, you will get a graph, a straight line, right? And its slope is negative. Remember that. Negative slope signifies, if you consider a point, when the voltage is high, suppose I am considering this point, when the voltage is high, current is less. When current is high, voltage is less. Inversely proportional relation, right? So if you draw the graph of this line, so you know this kind of a straight line having x by a plus y by v. On x-axis, that is your I, so I by SCC. I by SCC plus V by OCV. V by OCV is equals to 1. Clear? So now, guys, V by OCV, V by OCV is equals to 1 minus I by SCC. Means V is equals to OCV minus OCV by OCV by SCC into I. So this is the very famous formula, guys. Remember that whenever you have you need to solve the numericals. So V is equals to OCV minus OCV upon SCC into I. This is the very famous relation between the transformer voltage and the transformer current, right? And these two values are always given in the problems, OCV and SCV. Generally given. Sometimes they ask you to find out these two values. Some other datas are given, right? So where you can write where V is your transformer voltage, and I is equals to your transformer current. transformer current. Okay, so guys, note down this part. This is the graph, transformer voltage and transformer current. Note down all of you. Clear everyone? I hope this is clear. Naveen, clear Naveen? Good. Now, shall we proceed to the next part of the discussion, everyone? OCV minus OCV by SCC into I. Then all of you tell me. Clear everyone? Clear, good. Now see, now for any stable arc, remember, for any stable arc, for any stable arc condition, for a stable arc condition, remember that arc voltage is equals to transformer voltage. Arc voltage is what, your A plus Bn, and transformer voltage is your OCV minus, right? A plus Bn, OCV minus OCV to pi for stable arc. So while solving numerical, you can use always to solve any numericals of gate, engineering services, civil service, right? Any of the exams, you can directly, if it is not mentioned in the problems that take stable arc condition, by default you can assume stable arc condition and equate these two. Now, guys, whenever we do welding, our objective is to get maximum power so that maximum welding rate will be there, right? And the metal get melted in a rapid manner. So guys, how can we get the maximum welding power? And what are the conditions of maximum welding power? See, I'm going to derive that. So my dear, welding power, welding power, we can denote it as a P. So here welding power is P. P is quite simple. P is equals to voltage into current, VI, right? So we have transformer voltage and transformer current. Whenever these two values are given, you can directly equate it and calculate, right? Put the value and get the answer. Now, but our objective is to get the maximum welding power condition. So to get maximum welding power, what we are going to do? Let's see. So power we know, and V voltage, and we know the voltage is what actually OCV minus OCV by SCC into I. So we can put the value of voltage here. That is your OCV minus OCV by SCC into I into I, right? Into I. So here what we can say, my dear, power is like this. So power is your OCV into I minus OCV by SCC into I square. Clear? So if I'm going to differentiate power with respect to the variable is I, dP by di, it is your OCV minus 2I OCV by SCC. So for maximum power condition, for maximum welding power, suppose if you don't put the value of V here, then in that case you have to put I in terms of V. Then the function will have only one variable voltage. So then in that case you can differentiate power with respect to the voltage. So there are different methods. Whatever variable you select in with respect to that variable, you need to differentiate the function. So here I have created the function in terms of current. So I am doing this. So for maximum welding power, this term is going to be 0. So minus 2I into OCV by SCC. OCV by SCC. So here 2I OCV upon SCC is equals to OCV, right? So this is going to be cancelled. So here I is equals to SCC by 2. If the working current that is supplied by the transformer is half of the short circuit current, then you will get the maximum power, right? Then you will get the maximum power, my dear. This is your I, optimum current, right? Half of the short circuit current. Note down this part, everyone. I is your SCC by 2. Please have a look and note down. And similarly, I'm giving you the task, everyone. Get the short circuit voltage, sorry, optimum voltage and optimum arc length. Okay, everyone find out what is the value of voltage for maximum power. Done everyone? Did you get it? See, so I we got, my dear. Once we got the I, so now we know that V is equals to what? OCV minus OCV by OCV by SCC into I. Now if we put the value of I here, OCV by SCC, I is your SCC by 2. Whenever you put this value, I is your SCC by 2. So in this case, this is cancelled. Voltage becomes OCV by 2. Right, means half of the short circuit open circuit voltage. Okay, so if guys I am talking about, I'm giving you a notes, right? This is a very important note for maximum power condition. Okay, you remember that for maximum power output, guys, uh, V optimum is equals to optimum voltage, that is your OCV by 2. I optimum is your SCC by 2, short circuit current by 2. And power, maximum power is your, if you multiply these two, means OCV into SCC by 4. Right. And your V optimum, whenever you equate A plus BL optimum, you are going to get optimum arc length, right? L optimum means V optimum is nothing but your OCV by 2. If you equate the arc voltage as OCV by 2, you are going to get the maximum arc length, optimum arc length. This is the condition for maximum power output. These all are the condition for. Note down everyone. Note down please. Clear all of you? Good job. Now, guys, we are going to do some problems. See, my dear, first problem. See, the arc length voltage characteristics is given by 24 plus 4L, right? Arc length and V is the voltage. The volt ampere characteristics. The volt ampere characteristics. See, volt, whenever arc length voltage characteristics means the relation between voltage and length. Volt ampere characteristics means the relation between V and I, right? Characteristics of a power source. Of a power source is a straight line. Is a straight line. Okay. With open circuit voltage. With open circuit voltage 80 volt and short circuit current 600 ampere. Determine option A, optimum arc length. Question B, optimum voltage. Option C, optimum current. And option D, maximum power. Very easy, everyone. Try this. Do it, everyone. Tell me, guys. Answer. Answer. Tell me, Naveen. Answer. Still not getting the answer, guys. Very good, very good. 4 mm. Very good. Quite easy problem. See, first, right. Short circuit current voltage. This is your open circuit voltage. Six hundred 600 by 2, right? Maximum power. What? 12,000 volt, right? Right. V is equals to 20 plus 4L. 4 mm. This is the right answer, right? 4 mm, 40 volt, 300. This is the right answer. Next question, everyone. See, arc is represented 20 plus. If the arc length Building operation varies between 6 mm. And the welding current, if the arc length in the welding operation varies between 4 mm to 6 mm and the welding current assume linear power source characteristic. Assume linear power source characteristics. Calculate open circuit voltage, short circuit. Find out everyone. Find out everyone. Here in this problem, we need to find out the open circuit voltage and the short circuit current. Arc length varies between this and welding current. Find out, guys. Naveen, Srivastav, everyone. 88 volt is the wrong answer, friend. 88 volt is the wrong answer. Again, try this. Quite easy problem, guys. See, guys, how can we solve this? Most of you are getting wrong answer. See, quite simple question. Quite simple, my dear. I have given you enough time. Now let me solve it. Guys, arc length varies from 4 mm to 6 mm. So suppose L1, if I am talking about, this is your 4 mm, and L2 is your 6 mm. So we have the arc length voltage character V is equals to 20 plus 4L. So V1 is equals to this is 20 plus 4L. Okay. So here 20 plus 4 into 4. Right. Okay, my dear. What is given? V is equals to 20 plus 4. This is given to you. Similarly, L2 you have, guys, 6 mm. So V2 is equals to 20 plus 4 into 6. This is your 36 volt and this is your 44 volt. Clear, guys? Now, if I'm going to show you the graph, guys, we have voltage 36 and next is your 44. 44 volt. Okay. And current we have, that is 450 and 550. So you can draw 450 and 550. Four 50 by 550. So guys, here you can see. So we know the graph is a graph with a negative slope. Okay. So negative slope, the coordinate line will be like this. Lesser voltage, higher current. Lesser current, higher voltage. Therefore, in this case, the points are like this. The voltage will be like this. This is the voltage. Okay. Now, when it intersects whenever this line actually intersects the y-axis, then you are going to get OCV. Then it intersects the x-axis, then you are going to get SCC, short circuit. So here what we the coordinate pair I can tell you that is 450 comma 44 volt, and here 550 comma 36. So that is the catch in this. And this is the coordinate. Means low voltage, for low voltage high current is there, for high current low voltage. That is the catch in this. Okay. Now you guys can use the equation. We have what the formula. E is equals to general formula OCV minus OCV by SCC into I. Okay. So here voltage is your suppose 44, OCV minus OCV by SCC into I. I is your for it is 450. 36 is equals to OCV minus OCV by SCC into 550. Okay. So here what we have, this is your minus, this is your minus, this is your plus. So here 44 minus 39, what we can say, it is 8, right? 8. 8 is equals to OCV by SCC into 100. So you have OCV by SCC. This value is your 8 by 100. Now put this value in any of the equation. Suppose I'm going to put it in equation number 1. So 44 is equals to OCV minus 8 by 100 into 450. 8 by 100 into 450. So guys, 36 OCV is equals to 36 plus 44. 80. 80 volt we are getting the open circuit voltage. Now whenever you put 80 here, short circuit current. If suppose you are going to put this value in this equation, so 80 or 8, 8 cancel, it is your 1000 ampere. Okay, this is going to be your final answer. Clear all of you? Clear all of you? Clear everyone? Note down this. Clear everyone? Shall we proceed to the next? Shall we proceed to the next question, guys? Shall we proceed to the next problem, guys? Great. Now see. Next question, guys. The current welding machine with open circuit voltage 80 volt and short circuit current 800 during welding. During the measured arc current The measured arc current is 500 ampere corresponding to 7 mm. What is the linear voltage and arc current? What is the linear voltage and arc length? Find out, guys. Here in this problem, what we have to find out? We have to find out the relation between voltage and arc length. And OCV and SCCs are given. Current and corresponding arc length are given. So this is also a very beautiful problem. Good. Find out, all of you. Please find out the answer. Which one is the correct answer, all of you? Done, everyone? Tell me the right answer. Srivastav Prathamesh, E is equals to 20 plus 2L you are saying. Okay. Other students? Good. Good, my dear. Good. Very good. Very good, everyone. Very good. Very good. Option number A. Amazing. 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 Very good, everyone. Now see guys, how can we solve this? Mukul Manpure, Srivastava, Prathamesh, all of you given the right answer. So here guys, we can solve it. See, in solution you can see, my dear. See, everyone. One more thing which I want to highlight. See guys, current is given here. Uh, hmm, OCV and SCC 80 and 800. Okay, OCV is your 80 volt. SCC is your 800 ampere. Very good. Next part of discussion is during welding with the machine, the measured arc current is means I1 500 ampere. Okay, corresponding to arc length of 5 mm. Arc length of L1 5 mm. I2 is your 460 ampere. L2 is your 7 mm. Now guys, what we can do, we can use the formula. V is equals to OCV minus OCV by SCC into I. Okay, so we can calculate V is your V1. V is your V voltage. Suppose V it is required. OCV we know that is your 80 minus 80 by 800. I is your 500 ampere. Okay. So for 500 ampere, we are going to get the voltage V1. Right. So V1, what we are going to get? This is going to be your 30 volt. Similarly, all of you tell me similarly. V2 is equals to 80 minus 80 by 800 into 460. We are going to get this as 46, 34 volt. Okay. Now, guys, see V1 and V2 we have. So here, what we can do, we can use this. V is equals to A plus BL. V is equals to A plus BL. So V is equals to V2, suppose 34, and A plus, that is 460 ampere current is for 7 mm. So 7B, that is the equation number 1. And next is your 30 volt. A plus B is your 5B. The two equations, two unknown, just subtract. It is going to get A cancel. This is equals to 4. 2B, B is equals to 2. When B is equals to 2, A is equals to what? 30 is equals to A plus 10. A is equals to 20. Therefore, E is equals to 20 plus 2L. This is the final answer. EMF or voltage, whatever you write, E is equals to 20 plus. Is that clear, everyone? Is this clear, my dear? Good. I hope this is clear. Now the next important part of discussion. See, guys, is that clear, everyone? Then we are going to discuss the next part. Done. Very good. Now see guys, welding efficiencies, concept of welding efficiency. Welding efficiencies guys, see. Let's understand. Start everyone. Shall I start? See guys, start. See, welding efficiency. Suppose I am having a sheet like this. Suppose this is the sheet. Right. This is the sheet, my dear. Suppose I am going to join it. This is the sheet, my dear. Okay. Right. Now see, this is the sheet, my dear. Okay. This sheet which we are going to join. So here everyone, let's understand. These are two sheets. The this is the height T and gap between the plate. This is the gap B. B is the gap between the plate. The thickness of the sheet and B is the gap between the plate. And I'm using an electrode, guys. Suppose this is the electrode which is coming like this. Suppose this is the electrode and it is moving. This is the electrode and it is moving with F speed. It is moving in this direction. The electrode is moving in this direction with F speed. F is the welding speed. Okay. And the electrode and this is connected with the electrode and this is the workpiece which is connected with a transformer, right? Okay. Okay. It is like this a transformer. Electrode and workpiece are connected with a transformer. Now let's understand. This is the voltage across the transformer and I is the current. I is the current, right? I is the current. Now everyone, let's understand. This is called your base metal, my dear. Base metal, right? Base metal, base sheet, base. Okay, base workpiece. So this area, if I'm talking about this area, this cross-sectional area, if I'm talking about, like this is the cross-sectional area, right? Your cross-sectional area of weld. Okay, this is called your AW. This is your B into T, right? Now, points I am going to highlight. T is your T is the your T is thickness of the sheet to be welded. Thickness of sheet to be welded. B is the gap between the plate. Gap between the sheets. AW is the cross-sectional area of the welded joint. Cross-sectional area of the joint. So AW, value of AW is your B into T. Right, this is the first formula. Second formula is, my dear, after AW, F is your welding speed. F is your welding speed, right? Its unit is in your mm. This unit is mm. This unit is your mm square, right? So this is your mm square. This is your mm per second. Okay. One more term which I am going to define, RM. RM is your rate of melting, the rate at which volume of the material melted per unit time, right? The volume of the material melted per unit time, that is your rate of melting. Volume, as the material get melted, same amount of material get welded. So melting and welding are synonyms, you can say, in welding operation. The volume of the material melted per unit time. Melted per unit time. Okay. Volume of the material melted per unit time. Now, volume of the material melted per unit time, or you can call the rate of melting, rate of welding. And it is also called a rate of welding. So this is your mm cube per second. Right. We can calculate this RM, quite simple. RM is your area of the weld into welding speed. Area of the weld is your B into T into F. B into T into F. Right. So here you can see the units. It is just like MRR, mm, mm per second, and the rate of melting is your cube per second, right? I hope this is clear. Have a look and note down, everyone. Rate of melting, till rate of melting, please note down. Very important part which I am discussing, guys. Clear, everyone? Clear, all of you? Done, very good. Now, the next part of discussion is, everyone see. Next part of discussion is, my dear. See, all of you. Clear, very good, everyone, very good. Now, the next part is, my dear. See, next part is rate of melting. We are done with the rate of melting now. Now, guys, see, See, now understanding of heat. See, sometimes VH is also given in the problem. VH is your volumetric heat. Remember that. VH is your volumetric heat. VH is your volumetric heat. This is in joule per mm cube. Amount of heat required to melt 1 mm cube of the material. This is usually given. Sometimes it will be like this. It is given like in the problem x joule per mm cube. 10 joule, 20 joule, it would be given to you, right? So therefore, if suppose you want to calculate, right? Now let's understand the heat. The first heat, that is called your Hg. Hg is total heat generated by the transformer. Total heat generated by the transformer. Right. This is also called your welding power. Hg is called your welding power. Called your welding power, my dear. See, this Hg you can calculate by using like this the formula. Either you can calculate like V into I, right? Or you can calculate if resistance is given I square R, and if time is also given, then you can use, my dear, VIT, and here I square RT. So this is the total heat generated. So guys, the unit of this is your watt, means joule per second, and the unit of this is your VIT, that is your joule, right? This is your joule because I have multiplied by time. So heat generated in arc welding, we use voltage into current. In resistance welding, resistance is given, we use I square R. If time is given, you can use I square RT, right? So remember, this is how we calculate Hg, heat generated. So suppose this transformer has generated I square RT amount of heat, V into I amount of heat that is generated by the transformer. Actually, what happened, my dear? This is the amount of heat you generated, but this total heat cannot be transferred to the welding positions. Suppose this is the base metal. Some of the heat may uh, extracted by the surroundings, right? The surrounding air, the air present outside this system. Okay. So therefore, the amount of heat transferred to this welding zone. Suppose this is your system, my dear. I'm going to tell you a thermodynamic system. I am going to make. Suppose this is a system. What is R in Hg? R is resistance. Resistance between the, suppose this is a thermodynamic system which I am talking about. Okay. So in this system is called your welding zone, welding position. So you have generated this amount of heat, but the heat transferred to this system, this thermodynamic system, the amount of heat transferred, this is called your HT, or it is called your heat input, right? So remember that one thing which I am writing here, HT, that is heat transferred to the weld position, जहां पर वेल्डिंग हो रहा है, the position at which welding takes place. Resistance between the plates, not the resistance between the plates, Srivastav Prathamesh, that will be given because two plates are in contact. Now there is a small gap between them, so therefore the resistance between that. Now heat transfer to the weld position. Okay, you can also like call it heat input, right? Heat input to the weld. Heat input to the weld position. So suppose I have generated 1000 joule of heat, but transfer only 700 joule of heat. So then the 300 joule of heat get transferred to outside the system. This is a system, and surrounding is what, the base metal. So whenever welding takes place, you if you touch the base metal, you can see it's already heat up, right? So you can see some amount of heat get transferred to the base metal along with the welding position. So the what are the amount of heat which is transferred to the base metal? That is Hg minus Ht, right? So similarly here, one efficiency is defined, that is called your heat transfer efficiency. Heat transfer efficiency, or it is called your arc efficiency. Arc efficiency, right? It is actually the ratio of amount of heat transferred upon total heat generated. Remember that. You can also call it heat input to the weld divided by heat generated. Okay, guys. Right, this is the heat transfer efficiency. Okay, suppose if I'm going to ask you what is heat input to the weld. Okay, heat generated I have called you in joule per second something. Achha, one more formula which I want to write. Heat generated, right, Hg. The unit of Hg is Vi. In Vi the unit is joule per second. But if they ask you heat generated in joule per mm, it will be your Vi by F. Remember that. Vi by F. Suppose I am dividing it by welding speed. So now you can see the unit of Vi is your joule per second, and welding speed unit is your per second. Per second cancel out. If sometimes in gate exam they ask you to find out the heat generated in joule per in joule per you use Vi by F, right? Vi by F. Similarly, if I am going to ask you what is the heat input to the weld, it is your heat transfer efficiency into heat generated, and heat input to the weld is heat transfer efficiency into Vi by F. Vi also you can put Vi and as well as Vi by F. So now the heat input to the weld, this formula is very famous and so many times problems has been asked from this. It is your joule per mm. So heat input to the weld in joule per mm, right? And here your arc efficiency, heat transfer efficiency, V is the voltage, I is current, and F is the welding speed in mm per. Clear everyone? Clear guys? Clear everyone? Good. Now see, now see, next point. See, now guys, text part of discussion is we got the heat input to the weld. Now the main thing is, suppose this is your system, and you want to melt it. So guys, suppose The amount of heat required to melt this joining surfaces, these two surfaces, it is suppose 300. The amount of heat you are transferring 700. Amount of heat you are producing 1000. Means the requirement of heat is 300 and you are producing 1000. So the remaining heat is going where? Hg minus hm, the amount of heat required to melt the surfaces, hm. So first let's understand hm, right? Amount of heat required to melt the joining surfaces, hm, right? hm we can calculate amount of heat required to melt the joining surfaces. Okay, so see, hm usually we calculate hm. The first formula to calculate hm is uh, see Rm, rate of melting you have, into volumetric heat, Vh. Rm into Vh. This is the first formula. Rm into Vh. Because volumetric heat, its unit is your mm cube per second, rate of melting. Right, this is the rate of melting is your mm cube per second. This is your joule per mm cube. So this is how, my dear guys, we are going to get this in joule per second. Right. So if in watt or joule per second you want hm, heat required to melt, so you can use this formula Rm into Vh. Now the next part is very important. Okay? Next we can calculate hm in joule like this. Because suppose if you want to melt something, so first you are going to raise its temperature mc delta T plus m into latent heat of melting, latent, okay, ml, sensible heat, latent heat plus sensible heat. So here m you can take common, c delta T, delta T is your what? That is melting temperature. Suppose iron, you are doing the welding of iron. Iron is initially at 25 degrees Celsius. So you can take 25 to 1535 degrees Celsius. So this will be sensible heat. Now there will be phase change. 1535 solid will go into 1535 liquid. Right. So that's why this is a sensible heat. MC delta T. Delta T is your melting temperature minus initial temperature, room temperature, plus latent heat of fusion. Fuse, latent heat of fusion, that will be given for the material. Right. If suppose in a state of mass, density of the material and volume is given, so you can use this also. Rho into V, C delta T, melting temperature minus initial temperature plus latent heat of fusion. Right. Latent heat of fusion. This is very, very important. So this is also one formula to calculate H. And here the unit of HM is in joule, not in joule per second. So take care of unit. Unit is very, very important, right? Unit is, my dear, very, very important. So there's two methods to get HM. So and there are three terms of heat here. One is your Hg, second is your HT, and third is your HM. So whenever you solve numerical, take care. All these three must be in same unit, either in joule or in joule per second, right? Either in joule or watt, right? So note down this part, everyone. That is heat required to melt Clear, everyone? Clear, all of you? Good. Now see, all of you. Next part. Clear, Mukulman Pure, very good. Now, guys, one more efficiency is defined here. That is called your melting efficiency. Melting efficiency. And it is called, it is also called welding efficiency sometimes. So here melting efficiency is actually the ratio of amount of heat required upon transferred, HM by HT, right? Amount of heat required upon transfer. Quite simple. In a very basic layman language, if you want to understand this, suppose you have the system has generated, the transformer has generated 1000 joule of energy. You transferred 700 joule, but the requirement was of only 300 joule. So here 300 by 700 is your heat transfer efficiency, and 700 by 1000 is your heat transfer efficiency. 300 by 700. Okay, remember that. Now, so it will be like this. Now, waste heat. Okay, amount of heat transferred to the base metal. Right. Heat dissipated to the base metal. It is important. Heat dissipated to the base metal. So remember, my dear, the amount of heat dissipated to the base metal is what? I have just given you example, 1000 joule of heat produced, but the requirement was of 300. Right. Now, some students having this confusion in mind, ki suppose, sir, when we have the requirement of only 300 joule to melt these surfaces, then why not we are transferring 300 joule by the transformer? Because everyone know 100% efficiency is not possible. If your need is 3 joule, 300 joule, you cannot produce 300 joule, right? Because we cannot transfer 100% of the energy. There will be some losses, right? And various factors are there in that losses. So guys, that's why it is not possible. So that's why whatever I'm teaching you, take care of this. So suppose 100,000 joule produced, 700 joule transferred, and 300 joule requirement. Means the amount of heat Hg minus Hm, right? Because the need was 300. Produced, what we have produced? We have produced, my dear, 1000. So 100 minus 300 means 700. That is the total amount of heat which is actually transferred to this base metal, this metal part. And by getting that heat, this material, Hm is the heat required. Right? You can also understand it in a other fashion. Suppose the total amount of heat generated is Hg. Hg minus T is first transferred, and then plus Ht minus Hm. This is transferred to the base metal. Right? So here you can cancel Ht. So Hg minus Hm. Whenever you do numerical, take care of this. Hg minus Hm is the amount of heat transferred to the base metal. Okay? Hg minus Hm. This is transferred to the base metal. This Hg minus Hm is transferred to the base metal, this metal part, right? Hg minus Hm is transferred. Okay? Both side, this side as well as this side. Now, Hg minus Hm is transferred to the base metal. Clear, guys? Now, one more point which I want to highlight in this. See, suppose melting efficiency into heat transfer is equals to your Hm. Clear? We can write this equation like this. And Ht, we know what is Ht, heat transferred. So a heat transferred equation we have. Ht is your what? Ht is your heat transfer efficiency into Hg. So heat transfer efficiency into Hg. Suppose I am going to put this melting efficiency into heat transfer efficiency into Hg is equals to Hm. Right. Melting efficiency into heat transfer efficiency is equals to Hm by Hg. This is the main formula, which is actually the backbone of welding efficiencies. This is the right. So we just eliminate the HT from discussion, right? Because whenever you calculate HT, it will become more complicated. So melting is the product of the two efficiencies. The product of the two efficiencies is nothing but very simple. The product of the two efficiencies is nothing but it is the ratio of amount of heat required by amount of heat generated, right? That is very, very simple. So this is the very important chapter. Clear, guys? Remember this one. Now, some special cases which I want to highlight. Special cases. Sometimes what happen that heat transfer efficiency is your one, right? Is 1 or 100%. In that case, melting efficiency will be your. You can directly calculate Hm by Hg. Directly calculate Hm by Hg. Okay. This is called your welding efficiency. Whenever heat transfer efficiency is not given, the welding efficiency is Hm by Hg. Just these two ratios. Okay. Please have a look and note down. Note down each and every point. Please. Done everyone? Clear everyone? Please share the chat. Please share chat. Clear everyone? Done? Clear, everyone? Okay. Thank you, everyone. See you tomorrow at the same timing. We'll do problems on resistance welding tomorrow. And today's session is I'm going to end. Bye. Thank you.